Okay, welcome back everyone to another one of these tutorial videos on the theory of computation. So in this video, we'll be looking at an NP-complete reduction exercise, where in particular, we're asked to show that the independent set problem is NP-complete by using the fact that the vertex cover problem is NP-complete. So before we actually go through showing that independent set is in NP and is NP hard, let me just actually remind you of what these two decision problems are. So the independent set problem, which I'll abbreviate as IS, asks, given a graph G and some integer K, does G have an independent set of size K? Okay, so I mean, the key term here is independent set. What is an independent set? An independent set is a collection of vertices where for each pair of vertices in that set, in that subset of vertices, there's no edge between them, right? So all of the vertices in the subset of vertices are disconnected. So for instance, if we look at this graph here, then for instance, if we take this vertex and we place it into a set V prime, so maybe this is V1, this is V2, then V prime forms a 2 independent set because it has size 2, and V1 and V2 are not connected. There's no edge that's directly connecting them, okay? And in general, the definition of an independent set is some subset of the set of vertices in the graph, such that for every pair of vertices in V prime, V and U are disconnected. Of course, this is assuming that V is different from U, because, I mean, V is not disconnected from itself because it's itself, right? So that's the definition of an independent set. And so, for instance, here, the interesting thing about this graph is that we do have a 2 independent set, right? But we don't have a 3 independent set, right? Because if we were to have a 3 independent set, then you can examine this by splitting the graph into its sort of 3 clique subpart and the other 2 vertices. So for this part of the graph, there can only be at most one vertex in an independent set, because this is a sort of subgraph of G, which is completely connected, which is fully connected, right? So if I have 2 vertices in here that are in the independent set, then they're going to be connected, and so then I don't have a correct independent set. So that means at most one of these 3 vertices can be in an independent set. And then if I consider the other 2, then it can only be one of these 2, right? So that means, by arguing this way, I can only have an independent set of size at most 2 in here, right? And so not of size 3 or more. So that's the independent set problem. Now, what about the vertex cover problem, which I'll abbreviate as VC? So the vertex cover problem, again, assumes that we're given a graph and some integer k, and asks, does G have, of course, a vertex cover of size k? Now you might be asking, what is a vertex cover? So a vertex cover is, again, a subset of vertices, but in this case, we want to create a subset of vertices such that they cover all of the edges of the graph. So for instance, these 3 vertices together, so V1, V2, and V3, so this set of vertices forms a 3-vertex cover. Why a 3-vertex cover? Because, 3 because it has size 3. Why is it a vertex cover? Because you can see that V1 covers these edges, V2 covers these edges, and V3 covers these edges. It's fine if there's like redundant coverage. In fact, it's sometimes unavoidable that you have redundant coverage. And so a bit more formally, we say that V prime is a subset of V and is a vertex cover if for every edge in the graph, there exists at least one vertex in V prime, which covers E. More formally, we just mean that we have at least one vertex where the edge is incident to that vertex, i.e. E is incident to V, right? So either we have, V is here and this is E, or V is here and this is E, right? Okay. Okay, and so this is the vertex cover problem. And maybe one other interesting thing that I want to mention about the vertex cover problem is that for this particular graph, it looks like I can get a 3-vertex cover, but I can't get a vertex cover of a smaller size, right? So I can't get a 2-vertex cover. Why? Because to cover this subgraph, this 3-clique, I need at least 2 vertices because all of the edges between all of the vertices exist. So then if I want to cover all of the edges, I need at least 2 vertices. So then for this part of the graph, I need 2 vertices. And then to cover these other 3 edges, or at least this edge, I need another vertex, right? So either this one or this one. In which case, I can sort of argue logically this way that I must have a vertex cover of size at least 3, and I can't have one of a smaller size, right? Okay. All right, so now that we're a bit more familiar with the vertex cover and independent set problem, and that I've changed location to improve my Wi-Fi, let's actually discuss how we might show that the independent set problem is NP-complete by using the fact that the vertex cover problem is NP-complete. So we want to show that the independent set problem is NP-complete. And so to do this, we first need to show that the independent set problem is in NP, and then that the independent set problem is NP hard, which given the instructions in the question, we should do by reducing it from the vertex cover problem in polynomial time. Okay, so independent set is in NP. What does that mean? That means that, if we're given a graph and we're given some guess of an independent set of size k, then in practice that means that we're given some subset of vertices, so V prime. This is sometimes called the guess or the certificate, right? And so how do we verify the guess in polynomial time, right? We have to verify, firstly, that V prime is of size k. That's pretty easy. You just count how many vertices you have in your set. So this will be, O of size of the graph G. Then we have to check that for every pair of vertices in V prime, so maybe for this one and this one, there does not exist an edge between them, right? And so that's like a double for loop kind of, so it runs in size of the, or number of the vertices squared, right? So checking that there does not exist an edge for every VU in V prime. If you do this with like a double for loop, so for one vertex in V prime and for a second vertex in V prime, check that there does not exist an edge between them. Then this runs in V squared time. And so altogether, this is indeed a polynomial time verification of the guess. So we are indeed in NP, right? Excellent. Very nice. Now, the second thing that we need to show is that we're NP hard, which is typically the harder part of the reduction. And in this case, we're explicitly told that we should use the fact that the vertex cover problem is NP complete, i.e., really we need to use the fact that it's NP hard to show NP hardness. Because if we show the reduction and we know that this is NP hard, then this will also be NP hard, right? Because that's the sort of standard way of reading reductions is you have some problem at some level of difficulty. The problem that's after the greater or equal is at least as difficult, if not more difficult than the problem on the left side, right? That's how you should be reading this inequality sign. Okay, so how are we going to do this? Well, remember in a reduction, to show that in this case VC reduces to IS, we want to create a VC solver using an independent set solver, right? So I have an independent set solver. And so if I want to create a VC solver using the independent set solver, I'm assuming that as input, I'm getting, a graph G and an integer K. I'm instance modifying it, right? So this is my instance modifier, which in this case should be polynomial in time because we want a polynomial time reduction. And this instance modification should convert G and K to some value, some graph G prime and some value K prime, such that the independent solver returns yes, if and only if the initial answer to the vertex cover problem was yes, right? Which is also the same as saying, if this was yes, then this should return yes. And if this was no, then this should return no. Okay, so we want to design, right? The goal is to design the instance modifier such that an answer to the vertex cover problem given G and K is yes, if and only if an answer to the independent set problem given G prime and K prime is yes, right? Okay, so how are we going to do this? Well, we're going to do this based on a very nifty observation. The observation is the following. So if I have my running example of a graph here, and I have some vertex cover of this graph, but really of any graph. So maybe let's do the one that we had before. So these three vertices. Oops. So this one, and this one, right? So I'm covering all of my edges, right? So this is a vertex cover of size 3, right? Then let's take the same graph, right? Let's copy it once. And let's consider the vertices outside of V prime. Vertex cover V prime of size 3. So that's, maybe V1, V2, V3. So now let's consider the vertices in V prime complement, right? So that are in V, but that are not in V prime. right? So there's two vertices because I have a total of 5 vertices in my graph here. So that's going to be this vertex and this vertex, right? And what I observe is that there is no edge, right? There does not exist an edge between this vertex and this vertex, right? Which means that this set here, right, this subset of V prime complement, is an independent set of G, right? Now it's just going to be of size total number of vertices minus 3, and so I have an independent set of size 2, right? And this isn't like a coincidence, right? The fact that I have an independent set of size 2 in G is because of how I pick the vertices, right? So these two vertices are in V prime complement, right? So there definitely can't be an edge between any vertices in V prime complement, because if that were true, right, if there was an edge between these two vertices, or for that matter, any vertices in V prime complement where V prime is a vertex cover of G, then this edge, right, would not be covered by the vertex cover, right? Because these two vertices are in V prime complement, right? So the only vertices that can see this edge are, the ones in V prime complement. So that means that this is an uncovered, right? An uncovered edge for the vertex cover if it truly exists in the graph, right? And so that tells us that if I did have a correct vertex cover to begin with, then there cannot be such an edge, right? And this argument just generalizes to any graph, right? And so that's the lemma that I'm going to state. So the lemma that I'm going to state is G has a vertex cover of size K if and only if G has an independent set of size the total number of vertices minus K, right? And we can kind of prove this based on the argument that I just gave for this particular example. So, going from left to right, suppose that G has a vertex cover V prime of size K. What does this mean? Well, suppose I have some blob G, which is a graph. It has vertices, right? Then let's color the vertices in V prime in pink, right? Now, the observation that we make here is if I pick, right? So if I pick any pair of vertices in V prime complement, so maybe these two vertices, so this is maybe U and this is maybe V, then there does not exist an edge in E which connects U and V, right? Why? Because otherwise, if there were an edge, right? Otherwise, if there were an edge, then the edge UV would not be covered by the vertex cover V prime, which would be a contradiction, right? Which would be a contradiction. This is my symbol for contradiction, because we assumed to begin with that V prime was a correct vertex cover, right? And so that means, right, that means that because I picked U and V as arbitrary elements in V prime complement, this implies that I can sort of generalize this arbitrary pair of elements to a for all. That means that for every U, V in V prime complement, I don't have an edge between U and V. assuming, provided of course that U and V are different, but this is like a detail. Right? And so that implies that sort of by definition of the independent set, that V prime complement is an independent set of G of size, right? So then if I want to compute the size of V prime complement, well, it's of size V minus the size of V prime, which is K, right? And so then that proves the sort of forward direction of the lemma. The backward direction is very similar, right? So I'll leave it as an exercise for you to check. Similar argument. Okay, and so that's very nice. Why is that very nice? Because that means that I can create an instance modification based on this lemma. So therefore, the instance modification becomes copy basically G and let K prime be the number of vertices minus K, right? Then I can argue the correctness of this reduction, right? Because I can say, the answer of the vertex cover instance GK is yes, if and only if G has a vertex cover of size K. Well, by the lemma, right? So this is by the lemma. This is true if and only if G has an independent set of size V minus K. And just like replacing G with G prime and V minus K with K prime, this is true if and only if G prime has an independent set of size K prime. And because we're taking G prime and K prime and feeding it to the independent set solver, then this is true if and only if the independent set solver, because we're assuming it's correct and it exists and it works, says yes, right? So this is true if and only if the answer to the independent set solver is yes, right? So we have a correct vertex cover solver, right? So therefore, our VC solver is correct. Now, is the instance modification in polynomial time? Well, yes, because what we're doing is we're just taking G and copying it, right? I mean, this operation is constant time. You're just taking a number and subtracting it. This is the most expensive operation, but it's, O of maybe V plus E, right? And the instance modification is polynomial in time, copying G to G prime is, if we're doing it in a very silly manner and we're not even using pointers or something like that, pointers as in like C++ pointers for memory saving and so on, then we have this runtime, which is very polynomial, right? And so what does that mean? That implies that I do indeed have that vertex cover reduces to in polynomial time the independent set problem. And so this shows that therefore independent set is in NP and is NP hard, which implies that independent set is NP complete, right? Nice. And so that's how you argue that the independent set problem is NP complete from the vertex cover problem. And I might have said this in previous videos already, but this sort of trick of observing some relationship between the two properties in the two decision problems is a classic way of going about these reductions. Okay, so hopefully this was useful. Thanks for stopping by, and see you in the next one.